The idea of differentiability is really getting at the idea of, if I have a particular function, can I find the derivative of that function at a certain point, or on a given interval, or over the entirety of that function? So our context is going to determine some things, but if we're talking about differentiability, we could be talking about one specific point. We could be talking about a single interval. We could be talking about over the entirety of the function. Now, graphically, what we mean by differentiability is, do I have a smooth curve, or do I have a sharp point? So here's what we mean by the difference between smooth and sharp. A smooth curve is something like, may look something like this. Sharp points, though, could be like an absolute value graph. Could be a graph that looks something like this. Comes out to a cusp. Right, we could have a point that looks something like that. And the major difference between the smooth curve and the sharp points really ties into the idea of limit. So let's talk about the limit of each of these potentially. If you were to consider the derivative of the left-hand side, or consider the slope of this, this could have, because it's going down, could have a slope of, say, -3. And since this portion of the graph is going up, it could have a slope of +3. So what we would say in this case, if this is the x value c, that the limit as x approaches c of our curve from the left is -3, but the limit as x approaches c from the right of our function is +3. And really this is the limit of the derivative. So since the limit of the derivatives are different, this is not differentiable at that point, because there are two different derivatives from either side. If we consider the same thing on our second curve, and I'll redraw our curve with what's called a cusp here. Notice that on the left-hand side of our sharp point, what's happening to the tangent lines is they're getting steeper and steeper and steeper and more negative, while the right-hand lines are, as we approach that point, are also getting steeper and steeper, but they have positive slopes. So again, if this is the point C, and we're talking about the derivative at C, the limit as x approaches C from the left of the derivative of our curve is -infinity, because the line's getting steeper and steeper and steeper to the left of C, while the limit as x approaches C from the right of our function is +infinity, because the line is getting steeper and steeper, but with a positive slope. So this function again is not differentiable, because the left-hand limit and the right-hand limit are not equal. Or we could write that out as the left-hand limit does not equal the right-hand limit. And here's the issue. Both of these curves we've considered are continuous, but they are not differentiable. So, just because something is continuous doesn't mean it is differentiable at a point. But the converse of that statement if something is differentiable, then it must be continuous. If something is differentiable at a point, then it must be continuous at that point. So sometimes it's easier for me to know if something is differentiable at a point, and if I know it's differentiable at that point, then it must also be continuous. Differentiability implies continuity, but continuity doesn't tell you anything about whether or not something is differentiable. Let's consider a few examples. We'll look at example A. And the question is, determine whether the function is continuous, differentiable, neither, or both at a given point. So in the graph of A, notice that at 3, the question is it differentiable at x equals 3? Well, it's not continuous at x equals 3 because the limits are different on the left and the right. And it's not differentiable at that point either because the slope on the left-hand side would be positive, the slope on the right-hand side would be negative, so we know the derivatives on either side would be different if they're not approaching the same slope, the same number. So it's not differentiable. The answer for this one would be neither. Let's consider example C. We have a semicircle looking thing, and it's got a point here. This is differentiable at this point because the tangent lines would be on either side of that point, 0, would be approaching the same slope. So I know it's differentiable, and because it's differentiable, I also know that it must be continuous as well. So this would be an example of both. Let's look at, example G, whose graph looks something like this. It reaches kind of a sharp point at 2. I know it's continuous because the limit of the function that I approach to could be a from both sides, and the function's value at 2 is a. But it's not differentiable, and it's not differentiable if we want to think about this in tangent lines. From the right, it looks like it's becoming a horizontal tangent. From the left, it's not getting closer and closer to horizontal, it's staying with a positive slope. So this is not differentiable, however it is continuous. So there'd be different ways of making sense of continuity at a point. In the final video for this section, we'll look at a few more examples involving differentiability.